in water so cold and dark that cold and dark no longer seem like conditions, but simply like the nature of things. Something drifts. Its body is the shape of a long, smooth cone, a torpedo tapering toward a pair of slow-moving fins at its base, each fin rippling in a steady, unhurried wave that moves from front to back like a breath, like a long exhale. The animal hangs in open water. No surface is visible above it. No floor is visible below. It exists in the middle of a column of ocean that stretches farther in every direction than any edge the animal will ever reach, and it is still, and it is the length of a small car, and it is alive. The mantle, the main body, the torpedo shape belongs to a female. It extends roughly 2 meters from its rounded anterior end to where the fins begin their slow flutter. The skin across it is smooth, slightly granular in texture, and cool to any imagined touch in the way that deep water is cool, not like the cold of a refrigerator or a winter morning, but the cold of a place that has never been warm, that has no memory of warmth, where the temperature is simply what the temperature is and has been for longer than any individual animal. In the half-imagined light of deep water, the mantle is a reddish-brown, a color that looks at this depth almost like no color at all, a darkening, a density in the darkness, a shape slightly more solid than the water around it. Hanging below and ahead of the mantle, spreading outward from a central point at the animal's head, are 8 arms. They are shorter than the body. They radiate evenly from around the central beak, and along their inner surfaces, arranged in 2 neat rows, are the suckers, circular, faintly cupped, each one ringed at its edge, with small, hard, serrated teeth made of chitin. The arms do not reach far. They gather. They are for holding, not for reaching, and their work is close, attentive work, the work of the final grip. For the reaching, for the distance, there are 2 other appendages entirely. The tentacles are retracted now. When retracted, they travel alongside the body, long and pale and compactly held, and they are easy to overlook, but they are not the same thing as arms. They are something different in kind, not just in length. Each one is a long, thin stalk that ends in a widened, flattened, sucker-bearing club, an expansion like a hand, like a pair of hands opening wide, like the splayed end of a reaching limb. And when these tentacles extend, they extend fast, with a speed that the rest of the animal's slow drifting gives no warning of. They shoot out, they reach. In the moment of a strike, they cover several times the length of the mantle in a fraction of a second, and the clubs at their tips make contact, and the suckers latch, and the prey does not get loose from that first grip. The clubs themselves are lined with suckers, larger and more densely packed than those on the arms. Each club sucker has that same chitinous ring at its edge, serrated, firm, and backward curving, and these rings are important in ways that go beyond their immediate mechanical function. They are hard. They resist digestion. They persist in environments where soft tissue does not, and because they come in sizes that predict the sizes of the animals that bore them, they have served as one of the few reliable windows into how large these animals can grow. A sucker ring, the diameter of a large shirt button, implies an animal of a certain length. A ring slightly wider implies more. The rings keep their evidence long after the animal that made them is entirely gone, and their implications accumulate, and they will become part of a long, slowly assembled picture of something that has never been easy to see. But here, in this water, the animal is simply present. It drifts at a depth where the word drift takes on a different weight, not the drift of a boat on a river, not a lazy surface movement, but the drift of an animal at rest in a medium that supports it completely, without effort, without any structure to lean against. Water surrounds it from every direction equally. Pressure surrounds it from every direction equally. It is supported as perfectly as any large animal can be supported anywhere on Earth, and because of the way its tissues are organized, soft, non-compressible, carrying a dissolved chemistry in its fluids that balances the pressure outside without requiring a gas-filled cavity to maintain buoyancy. The animal simply is where it is, weightless in the practical sense, at ease in the one environment it fits. Architeuthis dux is the name the science eventually gave to this animal. It comes from the Greek for ruling squid, though no one living at the depth where this creature lives is aware of any such hierarchy. The name arrived in the scientific literature in 1853, late, after centuries during which the animal existed as rumor and wreckage and improbable eyewitness report, and the name settled onto something that had been real all along. It belongs to the class Cephalopoda, that grouping of mollusks which includes octopuses and cuttlefish and nautiluses, animals that have taken the basic body plan of the soft-shelled mollusk and reorganized it around a set of grasping arms placed directly on the head. Cephalopoda means head-foot, and it describes the most visible thing about them: the arms, the tentacles, the active reaching business of the front end of the animal. But Architeuthis dux is distinguished from its relatives by the depth at which it lives, by the openness of the water it inhabits, by the length of its tentacles, and by a scale that has no equivalent in any other living member of the group. The female of the species grows larger than the male. The mantle alone, just the body, without the arms or the long feeding tentacles, can reach between 1 and 2.5 meters in the largest confirmed specimens. Add the arms, and the animal is longer. Add the 2 fully extended tentacles, and the total length can reach 12 to 13 meters. That is longer than a large moving truck. It is longer than 2 small cars placed end to end. But measurements of soft-bodied animals pulled from the sea, often recovered after death, often stretched or compressed by the process of recovery, are difficult to standardize, and the verified upper end of the range is worth sitting with, carefully rather than treating as a firm ceiling, because the question of maximum size is one to which the record does not yet provide a definitive answer. What the record does provide is a clear sense of the proportions of the body. The mantle is the bulk of it, that smooth, tapered, torpedo-shaped central mass from which the fins spread at the tail end, and the arms and tentacles radiate at the head end. The fins are not large. They are relatively small for the size of the animal, and they appear to serve primarily as stabilizers and gentle directional aids rather than as the main source of propulsion. Propulsion, when the animal needs it urgently, comes from jet expulsion, water drawn into the mantle cavity and expelled through a muscular siphon at force, driving the animal backward in a rapid burst. Most of the time, though, the fins simply undulate. They ripple in that slow, continuous wave, and the animal holds its position, or drifts gradually, or makes the kind of small adjustments in orientation that an animal makes when it is at rest, but not asleep, attentive but not alarmed. The arms extend forward from around the beak, and the beak is worth pausing on. At the center of the arm crown, hidden between the arms unless they spread apart, is a pair of hard, curved, dark jaws that look in structure remarkably like the beak of a parrot. The same hooked curve, the same compact, powerful design for cutting and tearing. This is a hard structure in an almost entirely soft animal. The beak is made of chitin, the same substance that forms insect exoskeletons and crustacean shells, and it is the hardest part of Architeuthis dux by a very large margin. When the animal dies and the soft tissue decomposes, the beak remains. It persists. It ends up in the stomachs of the animals that hunt and eat giant squid, and it survives digestion, and it accumulates in those stomachs in numbers, and each one is a record. And together they have told researchers a very great deal about how often giant squid are eaten and how large the eaten ones were. Behind the beak, inside the mantle, the esophagus runs through the brain, a narrow tube passing through the center of a toroidal brain, which is a ring-shaped structure through which the food canal passes before the food continues into the stomach. This is an unusual arrangement that places a physical constraint on what the animal can swallow whole, because anything too large to pass through the brain ring must first be processed by the beak and radula into smaller pieces. The radula is a ribbon of muscular tissue set with small backward-pointing denticles, and it works something like a conveyor belt, moving material from the beak inward toward the stomach. These are not glamorous structures. They are the quiet internal machinery of an animal that must eat and eat substantially, at depth, in darkness, without making the kind of expensive extended pursuit that would cost more energy than the prey returned. The blood of Architeuthis ducks is blue, not metaphorically, not faintly, genuinely, chemically blue, because the oxygen-carrying molecule dissolved in the blood of cephalopods is not hemoglobin, as it is in vertebrates, but hemocyanin, which uses copper atoms rather than iron to bind and transport oxygen, and copper-oxygenated blood is blue. The blue of it is not the bright arterial blue of illustrations, but a pale, translucent, slightly marine blue, the color of water in a shallow tide pool, or the sky just after the blue of day has begun to leave it. This blood runs through open sinuses in the body tissues, rather than through a fully closed circulatory system, and the animal has 3 hearts, one that pumps blood to the gills, and 2 more, the branchial hearts, that help maintain pressure in the gill circulation. 3 hearts working together in a body drifting in cold, dark water at depth. The skin across the mantle surface contains chromatophores. These are the structures that give shallow water cephalopods, octopuses and cuttlefish in particular, their ability to change color and pattern with extraordinary speed and precision. A chromatophore in a cuttlefish is a small elastic sac filled with pigment granules, controlled by muscles radiating outward from its edge, like the spokes of a wheel. When those muscles contract, the sac is stretched flat, and the pigment spreads visibly across a wide area. When the muscles relax, the sac contracts back into a small point, and the color effectively disappears. The system is fast, precise, and under direct neural control, which is why cephalopods can produce running waves of color and complex patterns across their skin in fractions of a second. In Architeuthis ducks, the chromatophores are present. The pigment is there. The skin does carry color, that reddish-brown, that occasional shift toward a darker, more purplish tone across the mantle surface. And the chromatophores do expand and contract in slow pulses that move across the skin in gentle, irregular waves. But the sophisticated chromatic communication and camouflage that characterize shallow water relatives appears to be reduced here. In water this deep, there is no sunlight to reflect, no background pattern to match, no visually hunting predator to evade through mimicry. The precise, high-speed chromatic ability that evolution has elaborated so extensively in coastal cephalopods has less work to do at this depth, and the evidence is that in Architeuthis the system is present but muted, maintained in some functional form, but no longer the central communication and defense system. It is for relatives living in well-lit water. What color the living animal actually displays in its natural environment, whether the slow shifts of the chromatophores carry any communicative function, Whether they are involuntary physiological responses to state or temperature, or whether they serve some other purpose not yet understood, is something no researcher has been able to study in detail. The animal lives at a depth where direct, sustained observation has been almost impossible to achieve, and nearly everything known about its soft tissue physiology comes from dead or dying specimens recovered at the surface, where the conditions of life at depth no longer apply and where the animal's biology begins to fail almost immediately. Living animals studied in the open ocean in their own environment number at the time of this writing in the very low single digits of documented encounters, and those encounters have been brief. The chromatophores pulse and shift in the dark, in cold water, 1,000 meters below any easy knowing, and what they are saying, if they are saying anything, the science has not yet been able to hear. The fins at the base of the mantle are worth returning to. Seen from slightly below and behind, the fins of a large Architeuthis extend outward from the very tip of the mantle, like a pair of low, wide wings attached at their center to a long, smooth fuselage. They are not large relative to the mantle's mass, not the great paired fins of a cuttlefish, which extend nearly the whole length of that animal's body and give it a precision of movement that borders on the extraordinary. The fins of the giant squid are compact, almost modest, and they ripple in the specific way that cephalopod fins ripple, not a single oscillation of the whole fin, but a running wave that passes continuously from one end of the fin to the other, creating a gentle, stable thrust that holds the animal in position or moves it slowly forward. The wave is slow enough to follow with the eye. It moves like something being thought rather than something being done, a slow decision extended over time, expressed not in any single moment, but in the quiet continuity of the whole undulation. Imagining the animal from above, from directly above, as though looking down through a vertical column of cold water, the body resolves into a long oval, narrow and smooth, with the faint spreading of the fin tips at the lower end, and the broader, vaguer spread of the arms at the upper end. The tentacles are not visible from this angle unless they extend, and at rest they are simply part of the body profile, flat against the mantle's length, adding to its drawn-out symmetry. The animal is not camouflaged in any conventional sense. It has no pattern designed for a background, no counter-shading calibrated to the quality of light at a particular depth. Its color is its color, reddish and dark, and in the darkness where it lives, color is only partly relevant, because what matters in this environment is not what the animal looks like, but what it can detect, and what it can detect is shaped by one extraordinary structure: the eye. Each eye of Architeuthis ducks can reach 27 centimeters across. That is slightly wider than a standard sheet of paper, turned to its short edge. It is the largest eye of any living animal on Earth, larger than any other fish, invertebrate, or marine mammal, larger than the eye of a blue whale, which is considerably larger than a human eye, but does not approach this. The diameter of 27 centimeters is a verified measurement from preserved specimens, and the intact living eye in a large animal may be comparable in its dimensions, though as with everything about this animal, the living condition is difficult to confirm directly. An eye this large is not large for the sake of it. Eyes are expensive to grow and maintain in the currency of energy and biological resources, and an eye of this size must be doing something a smaller eye cannot do. The lens of a giant squid's eye is a hard, dense sphere several centimeters across, far too large and rigid to change shape for focusing, as the human lens does. Instead, the eye focuses by moving the lens forward and back within the eye, the way a camera focuses by moving its glass. The retina lines the inner surface of the eye behind the lens, and at the scale of 27 centimeters, the retina is a very large surface, capable of collecting light from an extremely wide angle and funneling it to photoreceptors distributed across that surface. The photoreceptors of the giant squid eye are not organized into the sharp central focus and peripheral blur that characterize many vertebrate eyes. The resolution across the retina is more uniform, which suits an animal that may need to detect something approaching from any direction in a dark and structureless environment. And the eye is specifically sensitive to blue light, the blue wavelengths that penetrate deepest in ocean water, that diminish more slowly than any other part of the spectrum as depth increases, so that even at the edge of total darkness, there is still faintly a residue of deep blue remaining in the water column above. What the giant squid is thought to look for with these eyes, what the design of this enormous optical instrument is calibrated to detect, is not prey. Prey are found through other means, through the sensitivity of the arms and tentacles to vibration and chemical signal, perhaps through the detection of bioluminescence at close range. The eyes, positioned on the sides of the head and oriented outward and upward, are thought to be oriented toward a different kind of detection entirely. A large predator descending through deep water, a sperm whale, diving from the surface in a long spiraling descent through the mesopelagic zone, disturbs the bioluminescent organisms in its path. Those organisms, startled by pressure or contact, flash. The flashing moves ahead of the whale, a spreading disturbance of cold blue light, a pattern of disturbance that propagates down through the water column faster than the whale itself, and an eye calibrated to detect faint, blue spatially patterned light from above would detect this, would register the approaching whale as a moving constellation of cold blue disturbance long before the whale arrived. 27 centimeters of eye is in this framing an early warning system. It is an investment in time, seconds, perhaps tens of seconds, between detection and the need to respond. In an animal that moves relatively slowly through deep water and cannot sustain high-speed flight for long, a few additional seconds of warning carry real value. The eye did not develop in order to provide this warning. Development in this sense is not the right frame, because no individual animal develops toward a goal, and the history of a biological structure is not a story of purpose being approached, but of variation being retained when it happened to work. The eyes of Architeuthis are what they are, because animals with somewhat larger eyes, across many generations, fared somewhat better than animals with slightly smaller ones in the deep water they inhabited, and their descendants inherited those eyes, and that process continued for a very long time in very deep, very cold, very dark water, and the eye that resulted is 27 centimeters wide and oriented upward into a darkness that is not quite total. The darkness at the depth where giant squid are most commonly found is worth being precise about. There is no sunlight at 1,000 meters. Sunlight does not reach 1,000 meters. At 200 meters, there is still a faint diminished remainder of daylight, blue and dim, enough to navigate by, not enough to see color. At 500 meters, that remainder is so faint that it registers not as light in any ordinary sense, but as a barely perceptible differential between up and sideways, a directional gradient rather than illumination. At 1,000 meters, there is nothing from the surface. The only light at this depth is biological, the cold, brief blue-green flashing of bioluminescent organisms, lanternfish, copepods, dinoflagellates, jellies, siphonophores, and the dozens of other mesopelagic organisms that produce their own light through chemical reactions carried out in specialized cells. This light is intermittent, It moves. It is triggered by disturbance. It appears and disappears in ways that carry information, in the way that any pattern in an otherwise patternless environment carries information. Because contrast is meaning, and in absolute dark, any light at all is a signal. The giant squid's eye meets this environment and works with it. The lens is shaped for low light gathering. The retina is broad, the pupil, not a simple circular aperture, but a more complex structure suited to the light conditions it routinely encounters, opens wide in the dark and closes narrower in the very rare presence of brighter light. The whole optical apparatus is built for an environment in which light is the exception, in which every photon is information, in which the difference between detecting a disturbance at distance and failing to detect it might be the difference between a successful evasion and a prediction event. The eye is the most dramatic single feature of Archetythus ducks, the one feature that most dramatically marks the animal as having been shaped by this specific environment over a very long time, and it sits on the side of the head of a living animal in cold, dark water at depth, oriented outward and upward, watching nothing, watching everything, watching the faint blue residual of a world it has never needed to visit. Across the surface of the mantle, the chromatophores move in their slow, unremarked pulses. The color of the skin shifts slightly, a darker wash of reddish purple spreading across the anterior portion of the mantle, then fading back toward the background reddish brown, then shifting again at the posterior end in a slow, irregular wave that has no apparent pattern and no apparent audience. The fins undulate. The arms rest, loosely curved, their suckers facing inward toward the central axis of the arm crown, not grasping anything. The tentacles are still. The animal in this moment is not hunting. It is not fleeing. It is between things, as living animals often are, suspended in the long intervals between the events that interrupt their lives. The deep ocean offers very long intervals. There is very little to respond to at this depth compared to the productive, crowded shallows where things are always happening. No currents to fight, no light to track, no seasonal change to mark the passage of time, no surface weather penetrating to this depth in any form the animal would recognize. The water is cold, the water is dark. The water has been this cold and this dark at this depth for longer than the species has existed, and the animal fits it the way a key fits a lock, not because the animal was designed for it, but because what fits persists, and what persists continues, and what continues long enough eventually becomes the standard against which all the variations of the lineage are measured. The mantle drifts slightly in whatever current is moving through this part of the water column at this depth. It is not a surface current. It is not a tidal current. It is the slow, deep circulation of the ocean's interior, water moving in response to density differences created by temperature and salinity, water that has not been at the surface for centuries, in some cases, water carrying the chemical history of its long transit through the interior of the sea. This circulation is everywhere in the deep ocean. It moves at speeds too slow to feel, too slow to see, measurable only by tracking dissolved chemicals over time spans that outlast any individual research program. And through this slowly moving water, the giant squid drifts. The body is roughly neutral in the water. The specific mechanism of this neutrality is worth understanding because it shapes everything about how the animal lives. Many fish maintain their buoyancy using a gas-filled swim bladder, a chamber of air or metabolic gas that can be inflated or deflated to match the animal's density to the density of the water at whatever depth it happens to occupy. This system works well for fish that live within a relatively narrow depth range, but at extreme depths, the gas compression required to maintain a rigid swim bladder becomes physiologically prohibitive. The giant squid uses a different solution. Its body tissues are saturated with a solution of ammonium chloride, a compound that is lighter than seawater of the same volume, and therefore provides a lifting force that compensates for the weight of the animal's denser structures. Ammonium chloride tastes strongly of ammonia. It gives the flesh of giant squid a sharp, acrid quality that makes it unpalatable to humans and is thought to make it less attractive even to many marine predators. But it provides buoyancy at any depth without requiring a compressed gas chamber, and for an animal that may range across a significant span of the water column, this passive chemical buoyancy is more reliable and less costly than the active gas-based alternative. The gill chambers lie within the mantle cavity, a pair of feathery branching gills over which water circulates as the mantle contracts and expands, drawing oxygenated water in and expelling it. The oxygen extracted by these gills travels into the hemocyanin-bearing blood and is carried to the tissues. At the cold temperatures of the deep, metabolic demand is lower than it would be in warmer water, and the available oxygen, though reduced from surface levels, is sufficient. The animal is not straining, it is not laboring, it exists at a metabolic pace calibrated exactly to the cold, dark, slow world it inhabits, a pace so much quieter than the metabolic pace of a warm surface animal that the comparison is almost difficult to make. The two eyes on the sides of the head continue their quiet vigil. They do not move in their sockets the way human eyes move. The scanning, tracking, socially communicative motion of a human eye has no exact equivalent here. But the eyes are not static. They can orient. The whole head can orient, and the orientation of the eyes relative to the body shifts as the animal makes its small, slow adjustments of position and angle in the water. They face outward and slightly upward. The deep blue of the water above is the deepest, most uniform blue imaginable, a blue so far from the surface that the word blue begins to feel imprecise because there is not enough light remaining at this depth to produce what the word blue ordinarily means. And what is present is something more like the direction from which light would come if light were here, more like the memory of blue than the color itself. And the eye, 27 centimeters across, its dark lens carrying no reflection, its surface smooth and cold and curved, faces that direction. It faces the place where the light is almost gone. It is shaped in every dimension of its extraordinary construction to find the last of it, to detect in that near total darkness the faint, cold, moving constellations of disturbed bioluminescence that means something large is coming from above. The eye does not know this. Eyes do not know things. The eye is a structure, and the structure does what it was built by time and pressure to do, and what it does is watch the dark above the animal with a sensitivity that no other eye on Earth in any living species possesses at the same scale. An animal can be made by darkness, not by any one darkness, not by any particular night or trench or depth, but by the long accumulated pressure of an environment that has no light, by the sustained, ancient fact of existing in a place where every generation lives and dies without ever encountering the sun, where vision means something entirely different from what it means in the world of daylight, where the largest organ of perception is calibrated not to the spectrum of visible light, as most animals know it, but to its faintest residue, its deepest penetrating wavelengths, its most peripheral and attenuated presence. Over time, long time, deep time, time measured in the slow accumulation of one generation following the next, an animal's body reflects its world. The deep ocean made the giant squid in the same way that the deep ocean made everything else that lives at depth, by keeping what worked and releasing what did not, slowly, without intention, over a span of time that makes the history of any single observer irrelevant. The mantle drifts, the fins undulate. The eye holds its position in the cold dark, facing upward into water that has carried no sunlight since before the animal was born and will carry none after it is gone. The darkness is not hostile. It is simply what the world is at this depth, and the animal fits it, shaped by it, carrying it in every dimension of its body, in the size of its eye, in the chemistry of its blood, in the slow pulse of its chromatophores against skin that has never been seen in full light. The world it inhabits is as complete and as stable as any world on earth, and the animal is entirely at home in it, entirely expressed by it, and entirely quietly. There, in Bergen, in the year 1752, a bishop sat at a writing table beside a window that looked out over the harbor, and he wrote the word real. Outside, the sea was gray and wide and full of things he could not name. Inside, the candle was close, the ink was wet, and Eric Pontoppidan, Bishop of Bergen and natural philosopher of considerable seriousness, pressed his pen against the page and described with careful measured language an animal of enormous size that fishermen had been encountering in these waters for generations without anyone of sufficient authority choosing to believe them. He did not describe it as a monster. He did not reach for the old vocabulary of sea serpents and divine wrath. He described it the way a man describes a whale or an ox, as a finite thing, bounded by a body, living in a specific part of the world, eating specific food, behaving in consistent and therefore observable ways. The kraken, he wrote, was real, it was large, it was biological, and the people who reported seeing it were not in the main mistaken. This was not a small decision. It was the year 1752, and the line between the natural world and the world of legend was not drawn as cleanly as it would later seem. Learned men still argued about sea serpents in serious volumes. The boundaries of the known ocean were only a century removed from maps that placed dragons at their edges. For a bishop, a man whose authority depended in part on the existence of the miraculous, the inexplicable, the beyond rational, to sit down and write that the most famous sea monster in the Norse imagination was simply an animal required a particular kind of intellectual commitment. It required the willingness to look at a legend and say not that it was false, but that it was incomplete, that something real was underneath it, that the shape of the fear was roughly correct, even if the details had been stretched and warped by time and distance, and the ordinary human tendency to make large things larger in the telling. Outside his window, the harbor was quiet. The fishing boats sat low in the cold water, and somewhere beyond the harbor mouth, beneath the surface of a sea that was gray above and very dark below, an animal moved slowly through the middle water without knowing it had just been given a category. Pontoppidan's description was not precise by later standards. He wrote from fishermen's accounts, from the accumulated testimony of coastal people who had seen the creature at the surface or pulled its remnants from the water, entangled in their nets. He did not have a specimen. He did not have a beak or a tentacle or a preserved section of mantle to lay on a table and measure. What he had was pattern, the consistency of the reports across generations, the agreement on certain features across witnesses who had no reason to coordinate their stories. The eyes, always the eyes, the arms, always many and long, the enormous bulk of the body beneath the surface, always larger than what was visible above it. A bishop's training in the careful evaluation of testimony served him better here than a more purely speculative mind might have. He knew the difference between what many people report independently and what one person invents and others repeat. What he read in the fishermen's accounts had the texture of observation, not imagination, so he wrote it down. He placed it in a natural history of Norway alongside the ordinary animals of those waters. He gave it approximate dimensions, enormous but finite, and an approximate diet and an approximate behavior. He was wrong about many of the details. The kraken was not, as he described, an island-sized creature capable of capsizing ships by diving beneath them. He had the magnitude broadly right, and the specifics somewhat off, which is a very reasonable result for a man working from second-hand accounts of an animal no European naturalist had formally examined. He was doing what good science does at the edge of its evidence, gathering, sorting, committing to what the pattern suggests, while holding the fine points lightly. The window in Bergen looked out over open water. The water looked back. And between the two, in the narrow space of a man's careful attention, something that had been legend for centuries began its slow migration toward fact. The coastlines of Norway had been producing evidence for a very long time, not just fishermen's stories, though those were plentiful and old. Physical evidence, the hard curved remnants of enormous beaks washing ashore in rack lines or pulled up in fishing gear. The occasional partial body, soft and decomposing, too large to be any familiar animal, its arms trailing into the tide like the collapsed rigging of something that had been recently, briefly, enormous. Clergy wrote it down, natural philosophers wrote it down, local administrators wrote it down in their accounts of unusual coastal events. The written record along the Norwegian, Scottish, Irish, and Orkney coastlines goes back to at least the 13th century, and the animal described is always roughly the same: a very large, many-armed creature with eyes of startling size, encountered dead or dying at the surface, or glimpsed briefly from a boat before it descended. These were not fabrications. The bodies were real. The smell of them was real. The heavy, ammoniacal smell of a large cephalopod decaying in the cold, salt air, a smell that anyone who has stood near it does not forget and would not choose to invent. The weight was real. The hard, persistent remnant of the beak, which does not rot the way flesh does, and which turns up in stomach contents and beach rack alike, was a physical object that could be handled and measured and wondered over. These things existed. The intellectual problem was not that the evidence was absent. The problem was that there was no framework large enough to hold it. A large, soft-bodied animal without bones leaves almost nothing behind. The mantle, the arms, the tentacles, all of it softens and dissolves over days, leaving only the beak and the sucker rings, and in certain conditions, a ghostly stain of dark pigment on rock or sand. What washed ashore was almost always partial: a piece of tentacle thick as a man's forearm, a fragment of mantle skin still reddish-brown and pebbled where the chromatophores were, a beak that looked like nothing, so much as the beak of a parrot, scaled to a size no parrot had ever reached. Taken separately, none of these things assembled, obviously, into a single known animal. Taken together, across a long coastline and many centuries, they described something consistent. But consistency across centuries requires someone to collect, to compare, to set the accounts from Norway beside the accounts from Scotland, and ask whether they are the same account, repeated, of the same animal. That collecting work took a very long time. It happened mostly in letters and in margins and in the footnotes of natural histories that were themselves read only by a small circle of people. The knowledge existed, It circulated. It simply had no name and no specimen and no formal scientific standing, which in the centuries before Linnaeus meant that it existed in a kind of administrative limbo between the real and the legendary. It was too consistent and too frequently attested to be purely imaginary. It was too poorly documented and too rarely seen to be officially acknowledged. It waited. Scotland had its own records. Ireland had its own. Along the coasts of the Orkney Islands, where the sea runs cold and fast and very deep, not far from shore, fishermen had been encountering partial bodies and occasionally living animals at the surface for centuries. These communities had a practical relationship with the evidence. They did not need a natural philosopher to tell them the animal existed. They had pulled its remnants from their nets. They had seen its arms in the tide. What they lacked was the vocabulary and the institutional access to move their knowledge from the edge of the sea into the center of the scientific record, which was held in those centuries in cities far from any coastline where such animals ever appeared. The knowledge moved slowly inland. It moved in the letters of clergy to scholars. It moved in the accounts of travelers who collected unusual observations from coastal people as a kind of intellectual tourism. It moved in the form of the occasional pickled partial specimen transported in a barrel from a northern port to a university, arriving damaged, stinking, and barely recognizable, but still undeniably real. Each of these arrivals in the record is a small event. None of them alone was sufficient. Each of them contributed one more strand to a picture that was by the middle of the 18th century, dense enough with evidence that only the absence of a formal scientific framework prevented its resolution into a species. Pontoppidan had provided the framework's first rough edge. But framework alone is not enough. What science needs in the end is an object. The French naval and merchant logs of the Age of Exploration contain their own body of evidence, written in the careful, formal hand of men whose professional training inclined them toward precise observation. A ship's officer recording a maritime encounter in an official log is not a fisherman telling a story at the quayside. He is a man whose livelihood depends on accurate reporting, who knows that exaggeration is a professional liability, and who writes in a register designed to be believed by superiors who were not present. These logs, read now with the benefit of hindsight, describe encounters that would not be difficult to believe at all if the animal they describe had been formally described. A large creature seen at the surface, arms spread wide, eyes of startling size, visible from the deck of a ship, an arm reaching briefly above the waterline before the animal descended. The accounts are distributed across the Atlantic and the Pacific, written in French and Portuguese and Spanish and English, spanning 2 centuries of ocean-going commerce. They describe the same animal. None of the officers writing these accounts had access to the accounts written by the others. They were sailors in different centuries, on different ships, crossing different parts of the same ocean, and they saw the same thing and wrote it down in their own words. The words are different. The thing described is not. There is something specifically interesting about an encounter at the surface. The giant squid is not a surface animal. It lives in the deep cold water, well below the layer where ships travel and humans swim. When one appears at the surface, it is almost always because something has gone wrong. It is dying, or it has been driven up by something below it, or it is in the final stages of being caught. The surface encounters recorded in the naval logs are, in this sense, evidence of the animal at its most visible and least characteristic. The animal that was glimpsed briefly from a French merchant vessel in the mid-Atlantic in a year, now lost to specific memory, was not behaving normally. It was at the wrong depth, in the wrong light, briefly available to human observation before it descended or died, and yet that brief abnormal availability is what entered the record. The normal life of the animal, the hundreds of meters below, the cold and the dark, and the slow drift through water no ship's lantern ever reached, left no log entry because no one was there to write it. The record is therefore, from the beginning, a record of the animal's exceptions. It is a history of failures and strandings and wrong depth encounters, and the accidental visibility of a creature whose ordinary life is conducted in complete and permanent obscurity. This is not a deficiency of the record. It is what the record is, and understanding it as such, as a collection of exceptions rather than a sample of the normal, is important to holding the evidence correctly. The naval logs are real, the coastal strandings are real, the beaks and the fishing nets are real. None of them shows the animal as it actually lives. All of them show the animal as it is when the surface of the world intrudes on its depth, and it becomes briefly, reluctantly legible. Herman Melville understood something about this. In 1851, writing about sperm whales, with the thoroughness of a man who had sailed on whalers, and paid close attention to everything he saw and heard at sea, he described an encounter with what he called the great live squid, a vast, pale, formless mass heaving at the ocean's surface, its arms moving slowly in the air before it slipped back beneath the water and was gone. The description is brief. It appears in his novel as an omen, a piece of sea mythology that the sailors interpret with dread, but the natural history behind it is genuine. Melville had access to the same body of sailor accounts, the same coastal traditions, the same accumulated evidence from whaling logs and maritime testimony, and he rendered it with the specific texture of a real observation, the paleness, the slow movement, the scale of the thing against the open water. He did not invent the great live squid. He assembled it from the record of exceptions that existed in the literature available to him, and he placed it where it belonged, in open water, briefly at the surface, descending before it could be fully seen. The novel was published 2 years before Architeuthis dux received its scientific name. In Denmark, in 1853, a zoologist named Japetus Steenstrup had spent years assembling the scattered evidence. He had read the coastal accounts. He had examined descriptions of strandings. He had compared the beaks that periodically turned up in collections and private curiosity cabinets, and the occasional pickled fragment in a university natural history museum. And he had, at some point in his long, patient accumulation, come into possession of a specific object, a large chitinous beak recovered from a stranding on the coast of Jutland. Intact, unmistakably the beak of a cephalopod, and larger than any beak from any known squid species by a significant margin. The beak was hard and dark and curved. It was roughly the shape of a parrot's beak, scaled to the size of a large man's fist, with a sharpness at the tip that suggested an animal capable of taking substantial prey. It was not beautiful in the way that a shell is beautiful, or in the way that a feather is beautiful. It had the beauty of a tool, the specific, minimal beauty of something shaped entirely by what it needs to do, with no material wasted and no line unnecessary. It sat on his examination table in Copenhagen, and it was undeniably, physically, irrefutably real. Steenstrup presented his findings formally. He described the animal from its beak and from the accumulated evidence of the stranding record, reconstructing the body in the way a comparative anatomist reconstructs an animal from its remnants, by comparison with known relatives, by the logic of proportion, by the physical constraints that govern the relationship between a beak of given size and a body capable of bearing it. He gave it a name. He assigned it to the class Cephalopoda. He placed it in the family Archaetethidae, and he called it Archaetethius dux, the ruling squid, the great squid, the largest squid that science had yet formally acknowledged. It had been real for centuries. Now it was real in the specific way that science makes things real, named, described, placed in a system of relationships to other known organisms, addressable in the literature of a discipline that had, until that moment, possessed no formal address for it. The beak on the table in Copenhagen was not the animal, it was the remnant of an animal that had lived and died in water, many hundreds of feet deep, and had come ashore by whatever accident or exhaustion had brought it to the Jutland coast. The animal itself was still in the ocean, in numbers that no one could estimate, at depths that no one had yet visited, conducting the ordinary business of its life, in complete indifference to the name it had just received. But the name mattered. It gave the evidence a center. It gave subsequent encounters a category to enter. It made the next stranding not an isolated curiosity, but a data point in the continuing description of a species. The work of describing Archaetethes dux had, with Steinstrup's 1853 publication, officially begun. The following decades produced more bodies, more beaks, more partial specimens, more tentacles recovered from beaches and fishing gear, and increasingly from the stomachs of the one predator, large enough and deep diving enough to encounter them regularly. The strandings were not new, but the context was. A cephalopod arm washing ashore in Newfoundland in 1865 was no longer an unexplained piece of sea creature. It was, tentatively, a piece of Archaetethes. It had a name to go with it. Newfoundland, in the latter half of the 19th century, became a particularly productive site of encounters. The cold, deep water of the northwest Atlantic off Newfoundland's coast appears to be, or to have been in those decades, a place where giant squid occasionally came to the surface in numbers unusual for the species. Whether this represents a genuine concentration of animals or a quirk of oceanographic conditions that drove them to the surface, or simply the presence of many small fishing boats whose crews were paying close attention to the water, is not fully clear. What is clear is that the 1860s and 70s produced a series of encounters in those waters that yielded physical specimens, partial and whole, of a quality that had not previously been available. The fishermen who encountered them described animals of significant size. The descriptions are consistent with what the scientific record was beginning to assemble: long tentacles, large eyes, a body of considerable bulk, behavior that suggested confusion or distress at the surface. Some of the animals were captured, or attempted to be captured, with the ordinary tools available to small fishing boats: gaffs, knives, rope. These encounters were not easy or comfortable. A large cephalopod, even a distressed one, is a strong and difficult animal to handle. The arms adhere, the beak can inflict a significant wound, the ink released in quantity darkens the water and obscures everything. The fishermen who brought these animals to shore were doing something physically demanding and probably frightening, without any scientific motivation and without any sense that what they were handling was of unusual importance to anyone outside their immediate community. It was of unusual importance. The specimens that reached the hands of naturalists in those decades, partial, damaged, often poorly preserved, but present, provided the first real material with which the internal anatomy of Archaetethes could be examined. The mantle, the gladius, the internal stiffening structure that in squid replaces the external shell of their more ancient relatives, the arrangement of the arms around the central beak, the structure of the tentacular clubs, the dimensions of the suckers, and the sucker rings. None of this had been available from a beak alone. The specimens made the animal for the first time three-dimensional in a scientific sense. The zoologist who did the most systematic work with these Newfoundland specimens was an American named Addison Emery Verrill, working out of Yale, whose careful anatomical descriptions of the materials sent to him from the northeastern coast in the 1870s produced the most detailed published account of Architeuthis anatomy available in the 19th century. He worked from damaged, poorly preserved material under difficult conditions with the tools of 19th century zoology. Measurements, drawings, comparative anatomy, careful description. He produced a body of work that remained foundational to the field for decades. He was methodical, patient, and thorough, and the work he produced from unpromising material has the quality of all good science done at the edge of available evidence. It is better than the conditions under which it was produced had any right to produce. Among the material that reached him was connected to an image. In November of 1874, in the harbor city of St. John's, Newfoundland, a Church of England clergyman named Moses Harvey acquired a large giant squid, partly through purchase from fishermen who had captured it, and partly through the practical management of getting a very large, soft, deteriorating animal to a setting where it could be documented. He draped it over a circular wooden bathtub in a domestic interior. The arms trailed to the floor. The mantle was large and pale. The tentacles extended beyond the frame of the ordinary domestic setting in a way that made the scale of the animal unmistakably legible, and Harvey photographed it. The photograph entered the record with a force that no written description had managed. Written descriptions of giant squid had been available for decades. They were believed by some and doubted by others, questioned by those who had not seen the material, and considered, not entirely without reason, to be the product of exaggeration or wishful natural history. A photograph does not exaggerate. It records whatever is in front of it with indifferent precision. The pale, large, unmistakably real animal draped over the wooden tub in Harvey's photograph was not a story. It was a fact flattened into light and shadow on a photographic plate, reproducible, shareable, inarguable. It went to Verrill. It went into the scientific literature. It went in various reproductions into the popular press. The question of whether Architeuthis was real had, with Harvey's photograph, found its final answer. The animal had been real all along, of course. The beak on Steenstrup's table had been real. The arms in the fishing nets had been real. The accounts in the Norwegian clergyman's margin notes had been real. The great live squid in the waters of the mid-Atlantic had been real. Pontoppidin's carefully reasoned assertion in 1752 that the fishermen were not wrong had been real. What the photograph provided was not a new reality, but a new legibility, the specific, flat, reproducible legibility of an image that could be placed in front of anyone and could not be doubted by ordinary means. There is something quiet about the accumulation of this evidence over such a long time. Not dramatic, not sudden. Centuries of partial glimpses and coastal remnants and careful letters and marginal annotations slowly thickening into a body of knowledge that grew dense enough at last to support a formal description. The beak in Denmark, the specimens in Newfoundland, the photograph in Harvey's harbor study. Each of these is a station in a long, unhurried process of a large thing becoming known. The animal did not change. The ocean did not change. What changed was the gradual, painstaking accumulation of human attention brought to bear across centuries on something that lived too deep and too quietly to offer itself to easy observation. The kraken In Pontoppidin's writing was a real animal. In Steenstrup's taxonomy, it was a named species. In Harvey's photograph, it was a visible fact. Each of these translations, from legend to natural observation to scientific name to physical image, was a necessary step, and none of them could have been skipped. The legend was where the observation was held before the science was ready for it. The natural observation was where the material was assembled before the framework existed to organize it. The scientific name was where the framework locked around the material, making subsequent work coherent. The photograph was where the animal became, finally, democratically visible, available not just to those with access to the scientific literature or the coastal strandings, but to anyone who could hold a printed page. All of this happened before anyone had seen a living giant squid in its own environment. It happened before anyone had followed one below the surface. It happened before the submersibles and the cameras and the deep sea equipment that would eventually make it possible to descend to the depth where these animals live and observe them moving in the water as they actually move, which is nothing like the way a draped and deteriorating specimen on a wooden tub suggests. What Pontoppidin and Steenstrup and Harvey and Verrill and all the fishermen and clergymen and sailors who contributed their observations to this long record were assembling was a portrait of an animal constructed entirely from its absences and its remnants from the hard parts it left behind, from the surfaces it occasionally intruded upon, from the soft edges of its body, as it appeared briefly in the wrong depth and then descended again. It is a portrait drawn in negative space. It shows the shape of something by showing where it was not, and what it left behind, and what it looked like when it was dead or dying, and therefore briefly and unfortunately visible. The living animal, at depth, in the cold dark water where it is most itself, was still unseen. The record of centuries had produced a name, a taxonomy, a body of anatomical description, a set of dimensions, and one photograph of a dead specimen in a domestic setting. It had not produced a single image of the creature as it actually lived. But the name was enough to begin with. The name gathered all the centuries of prior observation into a single address. The beak recovered from a beach in Jutland, the arm tangled in a fishing net off the Orkneys, the pale bulk seen briefly from the deck of a merchant vessel in the Atlantic, the Norwegian fisherman's account of an enormous shape rising near his boat in cold northern water. All of these were now, retroactively, evidence of Architeuthis ducks. All of them pointed to the same animal. All of them were, in their own partial and imperfect way, correct. In Copenhagen, in 1853, Japetus Steenstrup set the beak down on the examination table after he had finished with it and looked at it for what was probably not the last time. It was dark and hard and curved. It was smaller than the animal it had come from. It was larger than anything from any squid anyone in that city had previously examined. It sat in the ordinary light of a naturalist workroom, the light of lamps, the light of a window onto a city street, the light of ordinary European morning, and it was as real and as ordinary as anything else on the table. A chisel, a measuring rule, a notebook open to a fresh page. Outside the window, somewhere in the distant north, in water that was cold and dark and hundreds of feet deep, the animal that the beak had come from was not there anymore, but animals like it were, moving slowly through the mesopelagic dark, drifting in the cold below the thermocline, carrying their own eyes, their own arms, their own hard beaks in the centers of their own bodies, waiting without intention for the slow work of human attention to reach them where they lived. The beak on the table was the beginning of that reaching. Dark and curved and undeniable, it had given the animal its first scientific name, and it had closed quietly and without ceremony the long distance between the legend and the fact. At 1,000 meters below the surface of the ocean, the water presses in from every direction at once, not violently, not with the sudden force of a wave or a current. It presses the way stone presses, evenly, completely, without pause or preference, every surface receiving its full share of an immense and continuous weight. 100 atmospheres. That is the pressure at that depth, and it does not feel like anything to the water itself, because the water has always been this way here, and everything that lives at this depth has built itself around this fact, so thoroughly that the pressure is not an obstacle, but a condition, as ordinary to the animals below as air is to the ones above. The water at that depth is cold, not the mild cold of a refrigerator or an autumn morning, but a deep and permanent cold that does not change with the season, does not shift with the weather, does not respond to anything that happens at the surface. Somewhere between 2 and 5 degrees Celsius, just above freezing, held there by the sheer mass and stability of the water column above and around it. This cold has been here for a very long time. It predates the ships that sail the surface. It predates the civilizations that built those ships. It is the cold of a place that has not seen sunlight in its present form since before there were eyes to register the difference, and it settles over everything down here with a quiet authority that nothing at the surface can interrupt or reach. There is no sound that would be recognizable as sound. There is no wind. There is no breaking of water on a shoreline, no rain hitting the surface from below, no creak of wood or rope or hull. What exists instead is a deep, low, intermittent presence, the far-off click and moan of the ocean itself moving, the faint passage of pressure waves from storms and shipping lanes miles above, arriving down here as a very slow and very gentle vibration that the water carries without urgency. It is not silence exactly. It is something older than silence, a kind of acoustic darkness that is its own complete condition. The light is gone. It was gone well before this depth. At 200 meters, sunlight had already thinned to perhaps 1% of its surface intensity, all its warmer wavelengths stripped away by the water above, leaving only the faint blue end of the spectrum to carry any distance at all. By the time the water reaches 600 meters, even that blue has become hypothetical, present in theory, absorbed in practice, reduced to a level that instruments can measure, but no vertebrate eye, unaided by evolution, would register as light. At 1,000 meters, there is nothing. The photons that left the sun 8 minutes ago have not reached this far. They will not. The darkness here is not the darkness of a room with the lights off, where eyes adjust and shapes slowly emerge from the gray. It is the darkness of a place where light has never arrived in the first place, absolute even, and entirely without gradation. Into this environment, over the long span of time during which life has been filling in the ocean's every available depth, one animal arrived that would grow to carry the largest eyes of any living creature on Earth. Not because large eyes are useful in the usual sense, not for reading, not for finding berries or tracking prey across open ground, but because at the particular depth where this animal lives, the only light that matters is the faint, cold bioluminescence produced by the bodies of other organisms, and the faint silhouette of a very large predator descending from above, backlit by whatever marginal glow persists at 600 meters. An eye 27 centimeters across can gather enough of that marginal glow to make a difference. It can detect the displaced blue where something large passes through the dim gradient overhead. It can catch a disturbance in the bioluminescent field that a smaller eye would miss entirely. In this darkness, every photon is information, and the giant squid has built itself to receive every photon it can. The body that carries those eyes is long and smooth and cold to the surface. The mantle, the main muscular tube that contains the organs, stretches several feet in a large individual, tapering toward a narrow trailing end where two small stabilizing fins move in slow, continuous undulation, keeping the animal oriented without the expenditure of speed. The 8 shorter arms trail forward from the head, and between them the 2 longer feeding tentacles hang loosely, capable of extending far beyond the arm's reach in a single fast strike, but at rest simply trailing in the cold. The whole animal at rest is nearly still. It does not patrol. It does not cruise. It holds its position in the water column with a minimum of effort, sustained by a buoyancy system that relies not on a gas-filled chamber, but on a reservoir of ammonium chloride, a solution lighter than seawater, distributed through the animal's tissues and coelom, offsetting the natural density of its flesh without requiring the animal to swim continuously to maintain depth. This is what neutral buoyancy feels like at 1,000 meters, the animal suspended in cold darkness, fins moving gently, arms hanging, eyes open, waiting. The zone where the giant squid spends most of its life has a name in oceanography. It is called the mesopelagic zone, and it extends from roughly 200 meters down to around 1,000 meters, bracketing the depth range where sunlight diminishes from a thin residue to nothing. Mesopelagic means middle water, middle sea, and that is exactly what it is, the layer between the lit surface and the lightless abyss below, neither one thing nor the other, carrying within it the compressed gradient of everything the ocean does to light and pressure and temperature as it deepens. It is home to an enormous diversity of life, most of it small and largely unknown, most of it spending its days hiding in the dark and its nights drifting up toward the surface to feed in the slightly more productive shallows, then descending again before dawn. The giant squid does not make this vertical migration. It stays down, patient and still, letting the dark work for it. The thermocline is a real and physical boundary, though no diver could see it passing through. Above it, the ocean's upper few hundred meters mix with each other through wind, wave action, and the absorption and release of solar heat, and the water temperature shifts seasonally, regionally, unpredictably. A warm surface current can change everything above the thermocline in a matter of days. Below it, almost nothing changes. The water that sits at 5 degrees Celsius below the main thermocline in the North Atlantic today sat at approximately 5 degrees Celsius below the main thermocline in the North Atlantic when the first humans built boats. The stability is the point. For an animal adapted to cold, high-pressure conditions, the thermocline is not a barrier, but a guarantee, a depth below which the environment becomes predictable, consistent, and reliable in a way that the surface world is not and has never been. At the boundary where the warmer, mixed surface layer gives way to the cold, stable mass below, the temperature drops quickly over a relatively short vertical distance. This transition does not feel abrupt from a distance. It is invisible from the air, invisible from a ship's deck, invisible from a satellite. But a creature passing through it vertically would feel the change clearly, the water going from merely cool to genuinely cold in the space of perhaps 100 meters, the pressure continuing to build, the last traces of sunlight falling away above. Below that boundary, the cold is even, the pressure is even, the darkness is complete, and the water has a chemical character all its own, low in oxygen relative to the surface, carrying dissolved salts and nutrients in particular concentrations, bearing the slow chemistry of organic matter falling from above in a continuous light rain of particles and fragments, sinking toward the floor and gradually decomposing along the way. This falling of organic material has its own name too. It is called marine snow, and from the perspective of the deep ocean, it is the primary connection between the lit world above and the dark world below. Dead phytoplankton, fragments of zooplankton, shed skins and shells, and mucus webs, the fecal pellets of copepods and krill, all of it drifting slowly downward through the water column, dispersing as it falls, feeding the organisms of the mesopelagic zone as it passes through them, and delivering to the deep ocean floor whatever remains after everything above has taken its share. The giant squid lives well above the floor, in the zone where this snow is still falling through its world, where the mesopelagic fish that feed on it are present in large numbers, and where the conditions are cold and dark and stable enough to sustain an animal of very large size. The fish the giant squid feeds on are themselves remarkable in their own quiet ways. Lanternfish are small, rarely more than a few inches long, but they exist in such extraordinary abundance in the mesopelagic zone that they are thought to represent one of the largest concentrations of vertebrate biomass anywhere in the ocean. They carry rows of photophores along their flanks, small organs that produce cold blue-green light, and they use this bioluminescence for communication, for camouflage against the faint, downwelling light above, and possibly for other purposes not yet understood. To a giant squid hovering at depth, a school of lanternfish passing through its sensory range would appear as a slow constellation of moving lights in the dark, a faint, scattered glow that disrupts the even blackness and signals the presence of food. The tentacles extend, the lights scatter. Some do not escape. Other mesopelagic fish, orange ruffy, certain species of hatchetfish, bristle mouths with their wide upturned mouths lined with fang-like teeth for catching what passes above them, occupy different parts of this zone, each at the depth that suits its particular needs. And the giant squid moves among them as a predator that does not need to chase. The feeding tentacles are fast enough to strike and retract before prey can respond to the pressure wave that precedes them. The arms close around what the tentacles catch. The beak begins its work. And then the squid settles again into stillness, patient in the dark, waiting for the next disturbance in the field of faint biological light that constitutes its entire sensory world. Oxygen is lower in this zone than at the surface or at the bottom. The oxygen minimum zone, which in many parts of the ocean occupies much of the mesopelagic depth range, represents a layer where bacterial decomposition of organic matter consumes dissolved oxygen faster than circulation can replenish it. For fish with efficient respiratory systems calibrated for well-oxygenated water, this layer is limiting, a depth below which they cannot venture without physiological cost. For architeuthis ducks, the evidence suggests a different relationship with oxygen. The giant squid appears capable of tolerating conditions that would drive fish toward shallower, better oxygenated water, which may confer a real advantage in a zone that other predators partially avoid. This is not a conscious strategy. The animal does not know the oxygen is low. Its tissues simply function in the conditions they find, and the conditions it finds at this depth are conditions it has been shaped over a long time to endure. The ocean is not uniform from place to place, even at these depths. The seafloor's topography, the patterns of large-scale circulation, the proximity of productive surface waters, all of these influence where mesopelagic life concentrates, and by extension, where the animals that feed on it are likely to gather. Seamounts and mid-ocean ridges create upwelling currents that bring cold, nutrient-rich water toward the surface, seeding productivity that eventually rains back down into the deep in the form of that slow, organic snowfall. Where this productivity is high at the surface, it is also high at depth, and the mesopelagic zone below such regions supports a denser population of organisms at every level. There is a chain of volcanic islands in the mid-Atlantic, sitting above deep and productive ocean water, positioned within the range of both the North Atlantic gyre and the cold, deep water currents that circulate far below it. The islands rise steeply from the seafloor, their underwater flanks dropping away into water that is dark and cold and rich with mesopelagic life. Sperm whales congregate here in numbers that researchers following them across decades have found consistent and impressive. The whales dive deep, as sperm whales do, spending long minutes at depths where no light reaches, then surfacing to breathe and dive again, following some internal map of where the food is most reliably concentrated. They are eating squid, large squid, and the concentration of sperm whale activity in this place has long suggested that beneath these islands, the population of giant squid is substantial, not just passing through, but resident, sustained by whatever combination of depth and cold and prey abundance the steep flanks of these seamounts and islands creates. This is the Azores, and they sit in the Atlantic roughly a third of the way between Portugal and the American coast, familiar enough to sailors across centuries, crossed by ships and mapped in detail, surrounded by water that contains, somewhere beneath the surface, more giant squid than almost any similar region in the ocean. From above, the Azores look like islands, green, volcanic, rising from a blue surface that in summer catches the light warmly and in winter turns gray and rough under the Atlantic storms that move through this region in long procession. The surface is what ships see. It is what pilots see from altitude. It is what photographs show. Below it, beginning at the point where the last warmth of the surface layer gives way to the cold below the thermocline, the world is entirely different, darker and colder, and more densely occupied by life than the blue surface water suggests. At 800 meters below those green islands, where the light has been gone for hundreds of meters already, where the pressure is 80 atmospheres and the temperature is 3 degrees Celsius, and the water moves in slow, deep currents that take years to complete a single circuit of the ocean basin, the giant squid lives in numbers that scientists have been working with some difficulty to estimate. The difficulty is the access. 800 meters is far below the reach of any conventional diving equipment. It is far below the depth at which a submarine will routinely loiter to observe. It is deep enough that the water above it constitutes a genuine barrier to direct observation, accessible only to instruments lowered on cables, autonomous vehicles sent down on pre-programmed paths, or the occasional deep-diving research submersible. The animal itself leaves very little trace at the surface. Its body, if it dies, dissolves or is consumed before it reaches shallow water in most cases. Its eggs have never been found in the wild in any quantity. Its mating behavior has never been directly observed. The evidence that it exists in abundance beneath the Azores and other productive mid-ocean regions comes largely from the animals that eat it, from the beaks recovered from sperm whale stomachs, the frequency and duration of deep sperm whale dives in this region, and the occasional stranded or freshly dead specimen washed up on a shoreline after a storm or a deep water event brought it unexpectedly to the surface. The strandings are infrequent, but not vanishingly rare. Over the centuries, from the coastlines of Portugal and Spain, and the Canary Islands and the Azores themselves, from the beaches of Newfoundland and New Zealand and South Africa and Norway, Giant squid have arrived on shore, massive, soft, already beginning the decomposition that their deep cold bodies undergo with disconcerting speed once exposed to warmer water and air. They arrive large. They arrive pale. The chromatophores in the skin that in life produce shifting, slow patterns of reddish brown and granular purple have lost their muscle tone and contracted into invisibility, leaving the skin looking washed out and slack, the dimensions of the animal visible, but the vitality gone. The mantle still holds its torpedo shape for a time, firm enough in death to convey the scale. The arms are still there, and the two feeding tentacles and the fins at the trailing end. The eyes, even emptied of life, are large enough to stop people where they stand. It is one thing to read a measurement. It is another thing to stand on a beach in Newfoundland or on the shore of the Azores and look at an eye 27 centimeters across, lying on a mat of wet sand at the waterline, dull now, deflated a little by the change in pressure, but unmistakably what it is, a single organ of the same general form as all vertebrate eyes, scaled up to a size that makes the category feel insufficient. The eye did not evolve to be looked at. It evolved to look, to gather the faint bioluminescent signatures of sperm whales descending from above, to register the slow drift of mesopelagic fish through the dark, to function in an environment where its extraordinary diameter made sense, and where nothing in the anatomy of the animal suggested that it would ever find itself on a sunlit beach in the context of human astonishment. It is there nonetheless, on the beach, having arrived from a world that the surface people standing around it have never visited and will almost certainly never visit, and it is large. The transition between the warm surface layer and the cold stable water below is one of the most important physical features of the ocean, and it is worth spending a moment with the exact quality of what it is. It is not a wall. It is not a sharp line that could be photographed from inside the water. It is more like a change in register, the way a room changes character when the temperature shifts, even when nothing visible has altered. The upper ocean is restless, variably lit, mixed by the energy of the surface. The lower water is still, in the particular way that an enclosed space far from any moving air is still. The stillness is complete. It is not the stillness of a held breath, but the stillness of something that has not needed to move in a very long time. And the giant squid lives below this threshold, in that stillness, in that cold sustained by the pressure that would crush an unprotected human body in seconds, and untroubled by it, as an animal is always untroubled by the conditions it was built for. The ammonium chloride that provides the giant squid's neutral buoyancy is worth noting not as a fact to be remembered, but as a quality of the animal's presence in the water. The solution is distributed through the tissues and the fluid-filled coelom, the body cavity, in a way that makes the animal's flesh lighter than it looks. Unlike a fish with a gas-filled swim bladder, which must adjust the volume of that bladder as it moves up or down in the water column, the giant squid's buoyancy system is essentially passive. It is part of the animal's basic chemistry, rather than an organ that requires active regulation. The animal does not think about its depth. It drifts to the level where its overall density matches the density of the surrounding water, and there it stays, hovering without effort in the cold and dark, its fins making slow adjustments, its arms hanging loosely, its eyes gathering what little there is to gather in a world that offers almost nothing to see. The mesopelagic zone is full of creatures doing versions of this same thing. Bristlemouths with their fang-lined jaws, anglerfish trailing their bioluminescent lures, viperfish with teeth too large for their mouths to fully close around, siphonophores extending their colony of specialized bodies for meters through the water column, all of them adapted to a world of cold and pressure and near total darkness, each one a different solution to the same basic problem of surviving in a place where energy is scarce, light is absent, and the only reliable resource is the slow rain of organic material falling from above, and the other organisms that have learned to intercept it at various depths. The giant squid is the largest predator in this zone, or close to it, and its size itself is part of the adaptation. A large body retains heat more efficiently than a small one in cold water, and a long reach on the feeding tentacles means that prey does not need to come very close before it is caught. The cold that surrounds the giant squid at depth is the same cold that has circulated through the deep ocean for millions of years. It is water that sank at the poles, in the North Atlantic, in the Weddell Sea off Antarctica, because cold water is denser than warm water, and dense water sinks and spreads across the ocean floor in slow, enormous rivers that take centuries to complete a circuit of the global ocean basin. The cold, deep water at 1,000 meters in the mid-Atlantic may have last been at the surface in the waters off Greenland or Iceland several centuries ago. It has spent all of that time moving slowly in the dark, carrying its dissolved chemistry, accumulating the organic traces of everything that has decomposed in the water above it, sustaining the cold and stable environment in which animals like the giant squid have lived for far longer than human civilization has existed to notice them. There is a quality to this deep cold water that is almost geological, not the cold of a season or a storm, but the cold of a process so large and so slow that it operates on the same time scale as the movement of continental plates or the gradual filling of ocean basins by sediment. The giant squid lives inside this process without awareness of it, as all animals live inside the physical processes that constitute their world. The cold is simply there, the pressure is simply there, the dark is simply there, and the animal that has been shaped by these three constants, cold, pressure, darkness, over the deep time during which its lineage has occupied this zone, is not dramatic or urgent about any of it. It is simply present and still and very large in a world that few things have ever directly observed. Below the Azores, at the depth where the water holds its cold and the pressure reaches 80 or 90 atmospheres, and the last trace of surface light has been gone for hundreds of meters, there is likely a giant squid hanging in the water right now. Not metaphorically, not as a probability to be weighed, as a physical fact, a large, soft-bodied animal with eyes as wide as dinner plates, its mantle held in slight tension by the muscle beneath the smooth skin, its chromatophores pulsing in the slow, subtle way that they do in the dark, its feeding tentacles hanging loosely below and between the shorter arms. It is not aware of the islands above it. It is not aware of the ships at the surface, or the fishing lines that occasionally reach down into the upper part of its zone, or the fact that somewhere on land there are people who have spent careers trying to document its existence and have only just recently managed to film it alive. It is aware of the faint bioluminescent movement in the water at the edge of its sensory range, and the slight pressure wave of something large approaching from far above, and the cold that holds it at the right depth, without effort. These are the relevant facts of its world. The islands themselves, seen from this depth, would be almost imperceptible, perhaps a very faint disturbance in the quality of the absolute dark above, a barely perceptible change in the shadow cast by the island's mass on the deep water below, but probably not even that. The volcanic flanks of the Azores drop steeply into the ocean, and at 800 meters, the bottom is still far below, and the island's mass is behind and above. The water in every direction is the same dark and the same cold. The animal in it does not distinguish between the ocean directly beneath the islands and the ocean 100 miles to the west. To the giant squid, there are no islands. There is only the water and the cold and the pressure and the dark and the slow drift of organic particles and the faint lights of small fish moving through its world and the distant approach of things much larger than itself. While the Azores sit above one of the most productive regions of the deep Atlantic, and that productivity sustains a community of life at depth that is, by the available evidence, substantial and long-standing. The deep cold water circulates beneath the islands. The flanks of the underwater volcanic structures create mild upwelling that enriches the water column, and the result is a zone where the giant squid population is dense enough to support the regular deep diving of the sperm whales that gather near the surface above. This is not a coincidence. It is an ecology, a set of relationships between physical conditions and biological communities that has been in place for a very long time and that continues in the dark and cold whether or not anyone above the surface is paying attention. The pressure at 1,000 meters, the cold that does not change, the darkness that has no gradation. These are not threats to the animal that lives there. They are the terms of its existence, as specific and as complete as the terms under which any living thing occupies the world it was shaped for. The giant squid does not find the deep ocean extreme. It finds it home. And somewhere below the green islands of the Azores, in water that is 3 degrees Celsius and 80 atmospheres, and absolutely without light, a large animal turns very slowly in the dark, its enormous eyes open, registering the faint glow of something small passing nearby, its whole vast body suspended in the cold stability of the deep ocean as it has been suspended, generation after generation, for longer than the islands above it have existed in their current form. The water holds it, the dark keeps it, the cold is even and old and entirely sufficient, and the ocean continues in every direction, deep and quiet, carrying its slow chemistry and its slow life and its enormous unhurried animals through the dark beneath the surface, as it has always done, as it will continue to do, without any need for the light that falls on the water above. In the open stomach of a sperm whale, among soft folds of pale digestive tissue still warm from the animal's body, there are hard things. They do not dissolve, they do not yield, while everything around them, the fish bones, the squid flesh, the softer cartilage of 100 encounters in the dark, breaks down into a nutrient slurry and passes through. These objects remain exactly as they were when they arrived. Curved and dark and dense as a knuckle, each one is the beak of a giant squid. There are dozens of them, sometimes, arranged on a surface beside the opened carcass, sorted into rows by the hands of a researcher who has seen this before and still pauses over the count. They make a kind of census. Each beak is a life. Each one entered this stomach at the end of a struggle that happened far below, in water too cold and dark for any record but this. Science has known about giant squid for well over a century and a half. It has named the animal, measured its arms, catalogued its anatomy, debated its range, but for most of that time, the most reliable archive of the creature's abundance was not a specimen jar or a research database. It was the gut of another animal entirely. The sperm whale, descending hundreds of meters on a single breath, navigating by the echoes of its own sound, in water where no light has ever reached, returned from its dives with evidence pressed into its body, in the contents of its stomach, in the wax of its head, and in the surface of its skin. Generations of researchers working at whaling stations and research vessels, and eventually at the sites of strandings on cold beaches, Learn to read that evidence carefully. What the whale carried up from the deep told a story that no direct observation could yet provide. And the story it told was that the giant squid existed in numbers large enough to sustain one of the largest predator populations on the planet. A sperm whale in the North Atlantic or the deep Pacific feeds almost entirely on cephalopods. Of the squid species it takes during a lifetime of deep dives, giant squid, Architeuthis ducks represent a significant fraction by mass, though not necessarily by number. The whale finds them in the mesopelagic and bathypelagic zones at depths between roughly 600 and 1,000 meters, during dives that can last over an hour on a single reserve of oxygen. How it finds them at all, in a darkness that admits no reflected light, is partly understood and partly not. The whale's sonar, a beam of focused biological sound produced in the massive spermaceti organ in its head, can illuminate a large, soft-bodied animal at distances of several hundred meters. The echo that returns from a giant squid hovering in the water column carries enough acoustic information for the whale to orient, to close the distance. To take the squid has no sonar of its own. Its enormous eyes, adapted to gather every photon of bioluminescent light in the surrounding water, are calibrated for a different kind of detection entirely. Against the whale's sonar in absolute darkness, those eyes offer nothing. By the time the squid becomes aware, in whatever way awareness functions in a cephalopod, the whale is already close. What happens in the next few moments is not well documented, because it happens in the dark at a depth that no submersible had visited with working cameras for most of the history that generated this evidence. The beaks and the stomach are the aftermath. They are, in the strict physical sense, indestructible relative to the environment they inhabit, chitinous, structurally analogous to a parrot's beak, harder than any other tissue on the squid's body, and chemically resistant to the acids and enzymes that dissolve everything else. A single beak from a large Architeuthis measures several centimeters across its widest curve. The upper and lower mandibles hook together at a point, like shears, and the edge of each is slightly serrated, designed by long evolutionary pressure to sever and manipulate prey, not to be severed or dissolved itself. When the squid is digested, the beak remains. When the whale surfaces and continues its life, the beak is still there, slowly accumulating company as more dives produce more meals. When the whale dies and is examined, the beaks are a record of dozens or hundreds of encounters, each one a downward journey to a depth most of the world will never see. The radula sits just behind the beak, inside the soft tissue of the squid's oral apparatus. It is a ribbon of muscular material, shorter than the beak assembly itself, but far more complex in its surface, lined with rows of fine backward curving denticles, small and densely packed, arranged so that their angle of inclination is always inward, toward the stomach. The motion is peristaltic and slow. Food that has been cut and grasped by the beak passes on to this ribbon, and the ribbon draws it inward in pulses, each row of denticles engaging briefly and then releasing, the whole surface moving in a wave that is both conveyor and grater. In the cold darkness where the squid feeds, this organ processes fish and smaller cephalopods with a quiet mechanical efficiency. It too is occasionally recovered from whale stomachs, though far less commonly than the beak. Softer, more susceptible to digestion, it survives only when the conditions inside the whale's gut favor preservation. When it does survive, its dimensions give researchers another measurement to add to the growing portrait of the animal that carried it. Among the hardest and most useful pieces of evidence the sperm whale carries, the sucker ring teeth occupy a particular place. Each sucker on the arms and tentacular clubs of a giant squid is lined along its inner margin with a ring of chitinous teeth, small, pale, circular, with a serrated or toothed inner edge that catches and holds rather than slides. They are no larger than a shirt button, most of them. Under a lens, they look almost architectural, precise, geometric, symmetrically organized around a central opening, their serrations regular as stitching. They are the part of the sucker that makes contact with prey, that penetrates or depresses the surface and prevents slippage. And because they are chitinous, like the beak, they resist digestion. They accumulate in whale stomachs alongside the beaks in much larger numbers. A single squid contributes hundreds of sucker ring teeth, and they have turned out to carry information that the beak alone cannot provide. The diameter of a sucker ring tooth correlates in a predictable way with the diameter of the sucker it lines. The diameter of the sucker correlates with the diameter of the arm or tentacular club that bears it. The diameter of the arm correlates with the overall size of the animal. The chain of inference is long, but each link in it has been tested against specimens of known dimensions, and the correlation holds well enough to be used as a measurement tool. A researcher with a collection of sucker ring teeth recovered from a whale's stomach can, without any other information, estimate the mantle length and total length of the squid that produced them. The estimates carry uncertainty. The chain of correlation has scatter at every link, but they are not guesses. They are measurements made at one remove from an archive assembled in the dark. What those measurements have sometimes suggested is a size larger than any confirmed specimen. Among the beaks recovered from sperm whale stomachs, a small fraction are substantially larger than any beak attached to a measured architethus. Among the sucker ring teeth, some recovered from the stomachs of large male sperm whales imply an animal of a size that has never been directly confirmed. Whether these belong to exceptionally large architethus individuals, to undescribed giant squid species, or to measurement error compounded through the inferential chain, no one can say with certainty. The evidence is fragmentary, the inference is indirect, and the animals that produced it have never been seen. What the beaks and sucker ring teeth establish beyond any reasonable doubt is that giant squid are abundant enough and large enough to sustain a sperm whale population distributed across entire ocean basins. What they suggest more tentatively is that the upper bound of the animal's size remains genuinely open. The skin of an adult sperm whale carries a different kind of record, rolling at the surface after a long dive, its flanks dark and barnacled and faintly luminous in the low light. The whale's body is marked with circles. They appear as pale, slightly raised scars, some of them faded to near invisibility after years of healing, others more recent, still faintly pink at their margins, still slightly textured where the tissue knitted together. They are scattered across the whale's skin in constellations without pattern, some isolated, some overlapping, most concentrated in the areas around the jaw and head that come into contact with large prey during a struggle. Each one is the mark of a sucker ring tooth pressed into the whale's hide by a giant squid resisting capture. The small scars, a few centimeters across, are common. They appear on nearly every mature sperm whale examined in detail. They represent encounters with squid of ordinary size, large animals, but within the range of confirmed architeuthis measurements, their sucker diameters consistent with squid that would fit within what the fossil and specimen record already implies. But among these common scars there are others. Circular marks 10 centimeters or more in diameter have been documented on the skin of large male sperm whales. A scar of 10 centimeters implies a sucker of 10 centimeters, which implies an arm of a certain girth, which implies an animal of a total size that extends well beyond the largest confirmed specimen measurements. The logic is the same inferential chain that runs through the sucker ring teeth recovered from whale stomachs, but it is written in skin instead of chemistry, and it is visible to anyone who looks closely at the right animal in the right light. The largest scars raise a question that has never been fully resolved. They could belong to exceptionally large individuals of Architeuthis ducks, simply the far end of a size distribution that the specimen record has not yet captured, because the specimen record is so thin. They could belong to animals of a different, undescribed species sharing the same depth range. They could represent some artifact of scar expansion, the skin growing as the whale grows, stretching a smaller, original mark into something that looks larger than it was. Each of these explanations has been proposed, and none has been definitively ruled out. The scar remains on the whale's skin, 10 centimeters wide, pale and slightly raised in the morning light, while the animal drifts at the surface, breathing slowly after a dive of 500 or 800 meters. It is the only evidence that will ever be available for whatever made it. A sperm whale descending from the surface enters a different physical world within the first few hundred meters. The light falls away in stages, the bright blues of the upper ocean giving way to a deep indigo, then to a faint, sourceless twilight, then to nothing. The whale's body is adapted to this descent in ways that would be fatal to almost any other air-breathing mammal. Its lungs partially collapse under the pressure, releasing oxygen into the bloodstream rather than trapping air in the alveoli. Its heart rate slows. Blood is redirected from the extremities to the brain and heart. The spermaceti organ in its massive head, a structure of waxy, oil-filled tissue that the whale can warm or cool to alter its density, serves as a fine buoyancy control at depth, allowing the animal to hover without constant swimming effort. At 600 or 700 meters, the whale levels out and moves forward through the dark. The giant squid at that depth is aware of the approach before it can see it. Not through vision. The eye is extraordinary, and in the presence of bioluminescence, it gathers light with a sensitivity that nothing at the surface could match. But the whale produces no bioluminescence, and in the absence of any light source, the eye cannot function. What the squid may detect is a pressure wave, the low, advancing disturbance of a large body moving through water, or perhaps in ways that are not fully understood, the acoustic energy the whale produces at those depths. By that point, the whale is already within striking range. Whether the squid attempts to flee, or turns to face the threat, or simply holds still in the hope that stillness is safer, the encounter ends in one of two ways. Either the whale takes the squid, and the beak eventually joins the archive in its stomach, or something about the encounter goes differently. The squid's arms contact the whale's head, its sucker ring teeth press into the skin, and for a moment the two largest invertebrate animals in the deep ocean are in direct contact, in complete darkness, at a depth where no one has ever been to watch. Most encounters end with the whale. The evidence from stomach contents and the body condition of stranded sperm whales makes this clear. Giant squid are a dietary staple, taken regularly in numbers that imply the whale is highly effective at capturing them. But the scars on the whale's skin are evidence that not every encounter is immediate, and that some giant squid, under some conditions, offer more resistance than others. Whether the largest scars represent exceptional individuals or exceptional struggles is a question the evidence cannot answer. What they establish is that the interaction is not passive on the squid's side, that an animal caught at the end of a sonar beam in absolute darkness does not simply yield, and that the marks it leaves on a whale's skin can persist for years, slowly fading, carried around the ocean basin as a kind of witness to something that happened once in the dark. The ammonium chloride that keeps a giant squid neutrally buoyant in the water column makes its flesh bitter, deeply unpalatable to most predators that might otherwise take it. It is one reason, possibly, that the sperm whale has become so specialized on this prey. The whale's digestive chemistry and its apparent tolerance for the alkaline compounds in squid tissue are not shared by most other large predators. Sharks and other large fish that might theoretically encounter Architeuthis at shallower depths appear to find the flesh unacceptable or difficult to process. The sperm whale does not. The relationship between these two animals, one a warm-blooded, air-breathing mammal that descended from land-dwelling ancestors and returned to the sea, the other a mollusk that never left the water and represents one of the most ancient surviving lineages of complex animal life, is not a recent development. Sperm whale teeth and the beaks of large squid appear in the fossil record in configurations that suggest this predator-prey dynamic has been stable for millions of years. The whale's brain, the largest of any animal that has ever lived, evolved in a lineage that hunts in the dark by sound. The giant squid's eye, the largest of any living animal, evolved in a lineage that lives in the dark and detects light that is barely there. These two extremes of sensory investment meet regularly at depth in the cold and have been meeting for a very long time. The giant squid, for its part, does not live solely as prey. Its own feeding record is written in the remains of deep-sea fish and smaller cephalopods found in its stomach when specimens are fresh enough to allow examination. Lanternfish are among the most commonly identified prey, small, vertically migrating fish that rise through the water column at night and descend again by day, following the deep scattering layer that marks the upper boundary of the mesopelagic zone. The squid takes them with tentacular strikes that extend well beyond the reach of its shorter arms, the two long feeding tentacles shooting outward and snapping closed around a fish before it can react. The strike is fast, the hold is tenacious, the sucker ring teeth engage, and the food is drawn back toward the beak, which cuts, and the radula, which conveys, and the stomach, which slowly processes. The giant squid does not pursue its prey over long distances. Its ammonium-based buoyancy makes it energetically costly to swim hard for extended periods. The ammonia that keeps it neutrally buoyant is metabolically expensive to maintain and offers poor fuel efficiency compared to the lipid-based buoyancy of many other deep-sea organisms. The better strategy, which the body of the animal appears to support, is to hover and wait. In the mesopelagic zone, where the deep scattering layer brings food to the squid rather than requiring the squid to find it, this strategy works. Pute to the giant squid occupies a position in the food web that looks from a certain angle almost perfectly designed, a large patient predator in a layer of the ocean rich enough in migrating prey to supply it, and deep enough that only one effective predator pursues it in return. The evidence that supports this picture comes from many directions, and none of it is complete. Stomach contents from freshly examined specimens, a small number because fresh specimens are rare, give direct evidence of diet. Beaks and sucker ring teeth recovered from whale stomachs give indirect evidence of abundance and size. Scars on whale skin give indirect evidence of the largest sizes reached and the mechanics of encounter. Stable isotope analysis of Architeuthis tissue applied to preserved specimens gives information about trophic level, where in the food web the animal feeds, and has generally confirmed that giant squid occupy a position consistent with feeding on mesopelagic fish and other mid-level predators. Fatty acid composition of the tissue has been used to infer geographic range and depth of feeding. None of these methods tells the whole story. Each illuminates one corner of an animal whose life in the deep has been observed, in real time, only a handful of times. The stomach of the sperm whale is, in this sense, the most productive research site that exists for giant squid biology. It is accessible at whaling stations during the decades when commercial whaling provided regular carcasses for examination, accessible now at the sites of mass strandings and the occasional single-stranded animal that comes to rest on a beach somewhere within reach of a research institution. Every stomach is a collection. Every beak and sucker ring tooth recovered from that collection is a data point. Over the past century and a half, the accumulation of these data points has produced an estimate of giant squid abundance in the global ocean that is striking in its scale. The sperm whale population, distributed across the world's deep ocean basins, consumes an estimated several 100 million tons of squid per year across all species. The fraction attributable to Architeuthis is uncertain, but the volume of beaks recovered and the size of those beaks, scaled against the mass of tissue each represents, implies a population large enough to sustain predation at that rate. An animal that almost no one has ever directly seen may exist in numbers far larger than most people would guess. At a whaling station in the mid-20th century, a researcher sorting through the stomach contents of a large sperm whale would have handled hundreds of beaks in a single afternoon. They would have measured the largest, noted the size distribution, set the outliers aside for comparison. The work was quiet and repetitive and carried out in the particular smell of cetacean tissue, rich, marine, a little sweet, in a way that does not translate to other contexts. The beaks themselves were odorless, or nearly so, hard and clean and precise. They were the most resolved objects in a space dominated by soft, digesting matter. A researcher picking up one of the larger ones, curved, dense, dark as an old nail, held in their palm the last physical trace of an animal that had lived its entire life in a darkness the researcher had never experienced. At a pressure the researcher's body could not have survived, eating fish in the cold by a method no one had filmed. The beak was a bridge. It connected one world to another, and it was the only bridge available. Along the flanks of a large male sperm whale, drifting at the surface, somewhere in the Pacific, breathing slowly after a dive, the scars are mostly faded. The oldest ones are almost invisible. A slightly different texture to the skin, a marginally different reflectance in direct sunlight. The newer ones are easier to find. Among them, on the thick skin above the lower jaw, there are several large circles. Each one was made by a sucker ring tooth, pressed in hard during a struggle, at depth, in the dark. The squid that made the largest of them, if the inferential chain holds, if the scar diameter translates accurately back through sucker size and arm girth and mantle proportion, was an animal of a size that has never been confirmed in a measured specimen. That animal is gone now, digested except for whatever beak it contributed to the whale's stomach, metabolized into the tissues of the whale's brain and muscle, distributed through the food web of the deep Pacific. The scar is the only part of it that remains in the world, fading slowly on the skin of an animal that is still alive and will carry this record of the encounter for years more, surfacing periodically into a light that the squid never saw, breathing air that the squid never needed. The question of maximum size in Architeuthis has occupied researchers for as long as the animal has been formally known. The largest confirmed specimens, measured directly from tip of mantle to end of extended tentacular clubs, reach somewhere between 12 and 13 meters in total length, with mantle lengths in the region of 2 to 2.5 meters. These are large animals. They are among the largest invertebrates on Earth. But the beaks and the scars suggest that something larger exists or has existed, somewhere in the cold water below, the levels where human technology has yet to make reliable observations. Whether the upper bound of the distribution is 20% larger than the confirmed record, or 50% or more, cannot be determined from the evidence currently available. The honest answer is that no one knows. The beaks in the whale's stomach point toward an answer, and so do the scars on the whale's skin, but neither points precisely enough to resolve the question. The ocean holds the answer, somewhere in its cold middle depths, in the bodies of animals that have never come to a surface and never will. What the sperm whale has given science is not a complete picture, but a glimpse into a part of the ocean's life that would otherwise be entirely invisible. The whaling era, with all its costs, produced a record of deep-sea biology that no other method of the time could have approached. The beaks and sucker-ring teeth recovered from those examinations are still being analyzed, their dimensions added to databases, their chemical composition subjected to isotope analysis, their size distributions modeled against population estimates. The strandings that continue to occur on beaches worldwide add new specimens to that record, each one examined as carefully as possible before the tissue degrades beyond use. And the scars on the living whales that still dive through the world's deep ocean are still accumulating, still being photographed and measured by researchers who follow sperm whale populations for years at a time. In a cold bay somewhere off the coast of a high-latitude island, in the gray morning light after a night of heavy swells, a sperm whale lies on its side in the shallows. It is very large. It has been here for some hours already. Researchers are on the beach, moving carefully in the shallow water, beginning the long and difficult process of examination before the tide comes in. When they reach the stomach, having worked through the outer tissues in stages, they will find beaks, dozens of them at least. Some will be small. Some will be medium-sized. A few may be large enough to measure carefully and set aside for further analysis. Each one will be bagged and labeled and eventually examined under a lens, its dimensions added to the record, its presence interpreted against the growing data set of every other beak recovered from every other sperm whale, examined in every other part of the ocean. The researcher who picks up the largest beak will feel its weight and its hardness, and will know, as all researchers in this field have known since the discipline began, that it came from an animal they have almost certainly never seen, living a life that remains largely beyond the reach of any tool yet available, patient in the cold dark, hovering in the water column, invisible to everything but the sound of the whale descending. The circular scars on the whale's skin will fade slowly over the years that follow. The whale will dive again and return from each dive with whatever it has taken. The evidence will accumulate in its stomach and inscribe itself on its skin, and it will carry all of it through the world's deep ocean, surfacing to breathe in the light, descending again into the dark, where the giant squid waits in the cold water, neither aware of being documented nor shaped in any way by the long, patient, indirect study that its existence has generated. The whale will move on, the water will close over the place where it dove, and somewhere below, at a depth where the pressure is even and the temperature is stable, and the light has been absent for longer than the species studying it has existed, the squid will hold its position in the water column, its arms folded in against its body, its great eyes open, waiting for something to move. In a house in St. John's, Newfoundland, in the autumn of 1874, a clergyman stood in his study beside a wooden tub and looked at something that had no business being in a domestic room. The animal draped over the tub was pale and enormous and soft, Its arms trailed down to the floor. Its skin, in the cold light of that northern morning, had taken on the color of old ivory, and the early photographic flash would later give it something close to a lunar whiteness, a flat, still brightness that made the creature look less like something recently pulled from the sea and more like something from a much older world that had only just arrived. The Reverend Moses Harvey had acquired the specimen from local fishermen who had found it stranded on the Newfoundland coast, and he understood, with the particular alertness of a man who had spent years paying close attention to the natural world around him, that what was lying in his study was not merely large, it was significant in a way that ordinary large things are not. He photographed it. The photograph survived, and because it survived, the animal that had spent its entire life in water 1,000 feet below the reach of any fishing line became for the first time an image that could be held and studied and passed from hand to hand without the original decaying in between. That image, once made, could not be unmade. The creature had entered the record. The American zoologist Addison Emery Verrill received material from Harvey's specimen and from others that followed, and he used what he found to place the animal formally in the scientific literature. The features that Verrill described, the proportions of the mantle, the arrangement and relative lengths of the arms, the structure of the tentacular clubs and their sucker-bearing surfaces, confirmed what the beak in a Danish zoologist's collection had suggested 2 decades before, that this was a real animal, a species, a definite and describable thing. The name attached to it was Architeuthis dux. It meant, in rough translation, ruling squid. The name was large enough to hold what it named, and it has not changed since. What Harvey's photograph gave the world was not simply a picture of a strange creature. It was the beginning of a different kind of knowing, a knowing that depends not on the presence of a trained observer at the exact moment and place of a stranding, but on a record that persists. A photograph does not decompose. It does not get carried back out by the tide. It does not require the testimony of a single witness who may or may not be believed. It sits, it waits. It accumulates meaning as more images arrive alongside it, each new one adding a dimension that the first could not have predicted. For the decades that followed Harvey's photograph, the record grew in exactly this slow way. Specimens arrived on beaches along the North Atlantic coast. A few were caught in trawling nets that had been set for other things and came up with something unexpected and enormous, tangled in them. Researchers measured what they could measure, described what they could describe, and preserved what the cold and the time and the chemistry of preservation allowed. The soft tissues rarely survived intact. The beaks and the sucker rings and the gladius, the long feather-shaped internal structure of cartilage that runs the length of the mantle and gives the body its shape, these persisted. The rest dissolved or dried or collapsed into something that no longer resembled the living animal. What the specimens could not give, and what the photographs of stranded animals could not give, was any sense of what the animal was like when it was alive. The posture, the color, the quality of movement, the way it occupied the water column in the dark, all of this remained unknown. A stranded Architeuthis is an Architeuthis in the worst possible condition for observation. It has already failed. It is already in the process of returning to the basic elements it was assembled from. The creature in Harvey's photograph, pale and still against the wooden tub, was giving the world everything it had left to give, which was its shape and its scale, and a faint chemical trace of what it had been. The water it had come from was giving nothing at all. There is a depth in the ocean at which the last trace of sunlight, already attenuated to a faint, cold blue, by the time it reaches 200 feet, disappears entirely. Below this boundary, the water is dark in a way that has no equivalent on the surface of the earth. Not the darkness of a moonless night, which still holds the memory of sky. Not the darkness of a windowless room, which still holds the memory of electricity and architecture. The darkness below the light's reach is the original condition, older than eyes, older than anything that needed to know where it was going. It is not an absence so much as a presence, a medium with its own character, cold, still, enormously pressured, and complete. In this darkness, for the better part of a century and a half after Harvey's photograph, Architeuthis dux continued its life without interruption and almost entirely without witnesses. Specimens continued to appear at the surface or on beaches when something went wrong for an individual animal. Beaks continued to accumulate in sperm whale stomachs, recovered by researchers at necropsy stations and whaling facilities, and eventually sorted, measured, and added to the count of how many squid a single whale had consumed across its lifetime. Sucker ring scars continued to mark the flanks of whales hauled onto processing decks, their diameters recorded and converted through the mathematics of known scaling relationships into estimates of body size. All of this was evidence. All of it was genuine. None of it was the animal in the water. Two Japanese marine biologists changed this. Their names were Tsunemi Kubodera and Kyoichi Mori, and the method they used was patient, methodical, and in retrospect almost elegant in its simplicity. They knew that sperm whales fed in a specific region of the North Pacific, near the Ogasawara Islands, at depths broadly consistent with where giant squid were expected to live. They knew that any camera system lowered to those depths would need to be autonomous, since the presence of a large crewed submersible would almost certainly alter the behavior of any animal in the vicinity. And they knew that the lure would need to produce light, not the broad white light of a conventional underwater flash, but something smaller and stranger, more like the faint biological signals that travel through the deep ocean as food information. In September of 2004, they lowered an automated camera rig to approximately 900 meters depth. The rig held still in the dark for hours at a time. The bioluminescent lure pulsed below it in the cold water, producing the specific kind of light disturbance that the deep ocean uses as a language between organisms. And then, after 4 hours and 21 minutes, something came. It came in from the edge of the frame. It moved with deliberate, directed purpose, not the aimless drift of a neutrally buoyant organism going wherever the current takes it, but the particular quality of motion that belongs to an animal that has oriented itself towards something and decided to close the distance. The tentacles extended. They made contact with the lure. What followed was a struggle that lasted by the record of the camera, approximately 81 minutes, an engagement between the lure and the animal's grip that neither the lure nor the animal was willing to abandon without effort. When the rig was eventually hauled back to the surface, a piece of the animal came with it. A tentacular club, severed during the struggle, lay on the deck of the research vessel in daylight, pale, sucker-lined, soft, and enormous. When it was measured, it came to 5.5 meters. 5.5 meters of tissue from a single tentacle lying in ordinary surface light for the first time, its scale entirely incomprehensible against the railings and ropes and containers surrounding it. Kubodera and Mori had not brought up the animal, but what they had brought up was enough to confirm the depth, the behavior, the willingness to engage with something that produced bioluminescent light, and the scale of a living individual that had been there in that water 4 hours earlier. The still images the rig captured were the first photographs of a living giant squid taken in its natural environment. They showed the animal against absolute darkness, its arms and tentacles extended toward the lure, its mantle partially visible at the edge of the frame. The color was difficult to read in the available light. The posture was one of active engagement. The animal looked nothing like a stranded specimen. It looked like a predator that had made a decision and was carrying it out. Those images circulated through the scientific community and then through the wider world with a speed and reach that Harvey's photograph, produced in a different century, had never achieved. The deep ocean had yielded a picture. It was a partial picture taken in conditions that made every detail harder to read than anyone would have wished. But it was a picture of the living animal in its water, at its depth, doing the thing it actually did. The picture was real. The animal had not posed for it. The camera had simply been in the right place, in the dark, for long enough. The question that the 2004 photographs could not answer was the one that had been waiting since Harvey's tub. What did the animal actually look like when it moved freely through the water column? Not engaged with a lure, not partially visible at the edge of a frame, but simply present? What color was it? How did it hold itself? How did it move when it was not hunting? It took 8 more years, a new international collaboration, and a fundamentally different approach to cameras and light to produce an answer that was even partial. The submersible that carried the second camera system was modified to operate at depth in near darkness, using illumination in the near-infrared range of the spectrum, light that is invisible to most deep-sea organisms, which have evolved visual systems tuned to the blue wavelengths of bioluminescence and the residual sunlight that penetrates to mesopelagic depths. The logic was that near-infrared illumination would allow the camera to see without being seen, producing images of an undisturbed animal rather than an animal responding to an unexpected light source. The lure used was again bioluminescent, patterned after the specific optical signatures produced by disturbed deep-sea jellyfish, a signal that Architeuthis, with its enormous eyes calibrated for exactly this kind of faint blue light, would be likely to notice. In July of 2012, the team descended. The depth ranged between roughly 630 and 900 meters. The water at those depths was cold in the specific and total way that deep ocean water is cold, not the cold of weather, which comes and goes, but the cold of a medium that has been at 2 to 5 degrees Celsius for as long as the relevant water mass has existed, which is longer than any individual animal and longer than any measurable fraction of the species' history. The pressure at those depths was the pressure of 100 atmospheres pressing inward from every direction, simultaneously, and even an enormous weight that the animal's body had been shaped over evolutionary time to neither resist nor collapse under, but simply to be part of. The footage that came back lasted approximately 23 minutes in total. It showed a large Architeuthis ducks moving vertically through the water column, its body oriented with the mantle upright rather than horizontal, its fins moving in slow, even, unhurried strokes. The color of the animal, under the near-infrared illumination, appeared metallic. There was a quality to the surface of the mantle that no museum specimen had ever suggested, a faint sheen, almost golden in certain angles of the camera light, that had nothing to do with the reddish-brown of a preserved specimen and nothing to do with the pale ivory of a stranded one. The living animal, in its water, at its depth, was a different color entirely. It shone. The movement was equally unlike anything the specimens had implied. Stranded giant squid, and the photographs of stranded giant squid suggest an animal whose body is essentially passive, a long, soft structure that takes whatever shape gravity and the surface it rests on impose. The animal in the 2012 footage was the opposite of passive. Its fins controlled its position in the water column with what appeared to be continuous fine adjustment. Its body held its vertical orientation with the same kind of unconscious precision that a fish holds its depth, not through effort that is visible, but through a constant, automatic, entirely natural negotiation with the surrounding medium. The arms were held differently than any two-dimensional illustration had shown. They were gathered together and extended downward from the mantle, trailing below the body rather than splaying outward from it, giving the animal in motion a silhouette that was narrower and more vertical than the radial star-shaped form of a squid diagrammed from above. It moved through the water column the way a very large animal moves when it has no reason to hurry, with a kind of massive, self-contained patience that belongs to animals that have never had to be fast in order to survive. 23 minutes. In exchange for everything that had gone before, the centuries of strandings and sailor accounts, the accumulation of beaks in whale stomachs, the slow building of a scientific picture from fragments and inference, and the patient mathematics of sucker ring diameters, the ocean returned 23 minutes of footage. It was not nothing. It was, by any measure, the most valuable 23 minutes of marine biology footage gathered in a generation, but it was also, in its own way, a reminder of the proportion. Architeuthis ducks had been living in the deep North Pacific for at least as long as the species had existed, which was at minimum hundreds of thousands of years. The ocean had been keeping it entirely to itself for that whole time. 23 minutes was what it chose to give back. The footage confirmed some things that the specimens had implied. The scale was real. This was a large animal, clearly, and its movement through the water column was the movement of something that had size as one of its primary attributes. The eyes were large and forward-oriented, watching the lure with an attention that was recognizable across the gap between cephalopod and primate as the attention of a mind engaged with a problem. The tentacles extended when the animal chose to approach the lure and retracted when it did not, a control over its own elongation that the stranded specimens, with their limp and trailing appendages, had never managed to convey. What the footage could not resolve was the question of how the animal spent most of its time. 23 minutes of footage, gathered during an encounter with a lure, showed an Architeuthis in a specific behavioral mode: alert, oriented, engaged. It did not show an Architeuthis at rest. It did not show one in the slow suspended drift that the ammonia-based buoyancy system makes metabolically possible, hovering in cold dark water with minimal expenditure, waiting, simply present in the water column in the way that very large, very deep animals sometimes appear to wait, without impatience and without obvious purpose. That mode of existence, if it is how Architeuthis spends the bulk of its time, has never been filmed. The camera arrived during a moment of activity and left before the activity resolved into something quieter. There is a kind of knowledge that comes from watching. There is another kind that comes from chemistry, and it is older in some ways and stranger in its implications, and it has been reshaping what is known about Architeuthis since the early years of this century. In 2013, a team of geneticists led by Inger Winkelmann analyzed the mitochondrial DNA of 43 giant squid specimens gathered from ocean basins around the world: the North Atlantic, the South Atlantic, the North Pacific, the South Pacific, the waters around New Zealand and South Africa and Japan and the British Isles. The specimens came from strandings and from the stomachs of sperm whales and from trawling nets, and from research collections that had been accumulating material for decades, each individual tagged with its location and, where possible, its estimated size. 43 individuals representing the most geographically dispersed sample that had ever been assembled. What the analysis found was not what anyone had fully anticipated. The genetic diversity across all 43 specimens was extraordinarily low. Animals from opposite ends of the world, separated by the full breadth of ocean basins, were genetically nearly indistinguishable from one another. The variation between a giant squid caught off the coast of Newfoundland and one recovered from the stomach of a sperm whale in the South Pacific was smaller than the variation between populations of most large oceanic species across much smaller distances. The implication was clear, and it was significant, and it changed the picture in a way that the previous century and a half of physical specimen work had not been able to approach. There is, as far as the evidence can show, one species of giant squid in all the world's oceans, not a closely related cluster of species, each adapted to its own ocean basin, each with its own local population dynamics. One species. Architeuthis ducks moving through all the deep oceans simultaneously, maintaining a degree of genetic connectivity across distances that seem impossible for an animal with no documented migration behavior. The mechanism by which this connectivity is maintained is not fully understood. The best current picture suggests that Architeuthis larvae, small, planktonic, entirely unlike the adults they will become, may disperse across vast distances in surface and near-surface currents before descending to the depths where the adults live, carrying genetic material from one ocean basin to another in a slow, continuous exchange that the adult animals themselves may never undertake. This is a picture, not a confirmed account. The larvae of Architeuthis have almost never been reliably identified, but the genetics require some explanation for the connectivity, and larval dispersal is the one that fits. The low diversity also carries another implication, quieter and more uncertain. Populations with very low genetic diversity sometimes reflect the genetic signature of a past bottleneck, a point in the species' history when the population fell sharply, perhaps due to a change in ocean conditions or the loss of a major prey source, and then recovered. If such a bottleneck occurred in the history of Architeuthis ducks, the genetics alone cannot say when it happened or how severe it was. The deep past of a species is written in its DNA in a language that can be read only partially and only in the present. What was there before the bottleneck, if there was one, is not recoverable. The record, in this as in so many things, begins where it begins and not before. The water holds more. A Niskin bottle is a cylinder of metal and plastic, sealed at both ends by spring-loaded caps, designed to be lowered to a specific depth and then triggered to close, trapping a sample of the water column at that precise location. It is not a sophisticated instrument by the standards of modern oceanographic equipment. It is a container. It opens, fills, closes, and returns to the surface with whatever the water at that depth contained at the moment of sampling: dissolved gases, salts, particulate matter, the microscopic debris of biological activity that drifts through even the darkest and most apparently empty reaches of the ocean. Among the biological debris that a Niskin bottle can capture, if the depth is right and the filtration is fine enough and the molecular analysis is sensitive enough, are fragments of DNA shed by living organisms into the surrounding water, skin cells shed by the slow turnover of surface tissue, mucus extruded as a byproduct of normal physiology, gametes released into the water column in the ancient and persistent way of ocean reproduction, facies. the fine molecular residue of an organism's passage through a place, not the organism itself, but the invisible chemical fact of its having been there. This is what environmental DNA sampling collects. The technique, known in shorthand as eDNA sampling, applies the same logic to the deep ocean that archaeologists apply to ancient settlement sites when they look for traces of past habitation in the chemistry of the soil. Something was here. It left evidence. The evidence can be read. In the North Atlantic and the North Pacific, deep-sea water samples collected at depths consistent with Architeuthis habitat have returned genetic signatures that match the species specifically, not a close relative, not an ambiguous cephalopod signal, but Architeuthis ducks, the animal that the water was protecting, the one that the ocean had declined to show for most of recorded human history, was leaving itself behind in molecules too small to see. And those molecules, drawn up to the surface in a sealed cylinder and filtered through a membrane in a laboratory, were enough to say it was here, at this depth, in this water, at this time. The membrane on which those molecules settle is about the diameter of a coin. Under a microscope, it is a fine white disk of synthetic material, its surface smooth except for the particles that the filtration has deposited on it, bits of organic matter, faint discolorations that are the physical trace of biological passage, and somewhere in the irregularity of that surface, fragments of DNA too small to see directly, but large enough in their molecular specificity to carry a name. Architeuthis ducks, the ruling squid, the animal in the dark. What eDNA cannot give is a count. It confirms presence, not abundance. It says that the animal was in a volume of water at some point before the bottle was closed, but it cannot say how many animals, or how recently, or whether the signal represents a resident population or a single individual in transit through a corridor between feeding grounds. The technique is expanding, and the questions it can answer are slowly widening. But for now, the picture it gives is a picture of traces, the faint chemical autobiography of a creature that passed through and left the water changed in ways too subtle for any other method to read. There is something in this that feels consistent with everything else that is known about Architeuthis. The whole history of how the animal has been known is a history of traces, beaks in whale stomachs, scars on whale skin, severed tentacular clubs on research vessel decks, brief and partial sequences of footage gathered in moments of engagement with a lure. The animal has never permitted a sustained or comprehensive view. It has offered instead a long accumulation of edges, the beak, the sucker ring, the skin cell, the 23 minutes of metallic body moving through near-infrared light, and left the rest to inference and patience. The patience required to study Architeuthis ducks is of a specific kind. It is not the patience of waiting for something to happen in a situation where the outcome is uncertain, but the timeline is comprehensible. It is the patience of waiting in the dark for something that may not come, with equipment designed for a set of conditions that can never be fully tested before it is deployed, targeting a species whose behavior is almost entirely unknown and whose distribution is mapped largely from the stomachs of other animals. The researchers who have contributed most to what is now known about the giant squid have spent careers building toward encounters that lasted minutes or hours and then returned, with whatever the ocean chose to give, to begin the analysis that would take months or years. Kubadera returned to the Ogasawara Islands after the 2004 photographs. He returned again before the 2012 footage was gathered. The expeditions that did not produce footage or specimens were not failures in any meaningful sense. They were part of the accumulation that made the successes possible. The nights that the automated camera rig sat in darkness at 900 meters and recorded nothing but the faint movement of the water column were still nights during which equipment was tested and lure behavior was observed, and the specific conditions of that depth and that location became better understood. None of the nothing that was recorded was wasted. This is not a common way for evidence to accumulate. Most scientific fields advance through the logic of controlled experiment, where conditions are set and manipulated, and the results can be compared against a baseline. The study of Architecthus advances through the logic of encounter, of being in the right place, with working equipment, in conditions that happen to produce an animal willing to approach a lure, or strand itself on a beach, or leave a piece of itself behind in the water. The species cannot be bred in captivity. It cannot be tagged and tracked in the way that whale populations are tagged. It cannot be observed across its full behavioral range, because that range, whatever it is, takes place in a part of the ocean that is still beyond sustained, comfortable access. What has been learned despite all of this is not small. A species has been confirmed, one species present in every major ocean basin. A genetic signal has been extracted from the water itself. Footage exists. Living color is known. The posture in the water column has been observed. The behavior of engagement, the approach, the tentacle extension, the grip has been filmed. The scales of individuals recovered in the stomachs of sperm whales have been estimated, and the largest of those estimates suggest animals that approach or may exceed the dimensions of verified specimens. What has not been learned is, by any measure, larger. The breeding behavior of Architecthus ducks has never been observed. No mating, no spawning, no courtship, no parental behavior, none of it has been directly witnessed. The eggs of the species have been tentatively identified only from a small number of specimens. The larvae, if the larval dispersal hypothesis is correct, are moving through the world's surface oceans right now, unidentified in plankton toes, passing through nets that are looking for other things, completing a phase of the life cycle that no one has ever seen from beginning to end. The lifespan of an individual Architecthus is estimated on the basis of growth ring analysis in the hard structures that preserve over time to be somewhere between 3 and 5 years, a startlingly brief existence for such a large animal, if the estimates are correct. In 3 to 5 years, a creature grows from a planktonic larva to something that can leave 5-centimeter sucker ring scars on the skin of a sperm whale. That growth rate is not yet fully explained. The population size of the species globally is unknown. The seasonal and regional movements, if any exist, are unknown. The precise mechanism of the buoyancy system and the energetics of how the animal compensates for the metabolic costs of its ammonia-based density management are not fully characterized. The chromatophores in the skin, the pigment-filled elastic sacs that expand and contract in the skins of shallow water cephalopods to produce rapid, dramatic color changes, are present in Architecthus, but whether and how they function in the animal's dark environment, where no reflected light would carry their signals to any viewer, is an open question. The animal may be communicating in color in the dark, in patterns no one has ever seen, for reasons that have never been studied, or the chromatophores may be vestigial in the deep water context, a feature retained from a shallower evolutionary ancestor, functional in the tissue without being functional for the animal's current life. No one knows. A laboratory in Auckland holds a specimen of Architecthus ducks preserved in a tank of formaldehyde and salt water. The animal has been there for years. Researchers come to measure it, to take tissue samples from it, to study the anatomy of structures that are otherwise impossible to access.